Okay, this is my attempt to help Jacek out. So benchmarks are a great idea. It gives a level playing field and encourages vendors to have features that make your benchmark go fast. And basically, Jacek would like to see commercial systems do a lot better on LSST's workload. So this benchmark is an abstraction of LSST, which is an astronomy workload. Basically captures the essence of a whole bunch of other fields in addition to astronomy. So I think it's fairly general. Jacek's workload looks like this. Telescope takes this. Then what happens is that you end up doing a whole bunch of workflow downstream. So you want to capture the end-to-end processing from telescope to derived data products to queries. So basically, this benchmark is ingest a bunch of raw data, cook it into a bunch of derived data products. What that means is look for stars in these images, store the stars as observations and other kinds of celestial objects. And then if you point this telescope to the same place in the sky at some subsequent time, you'll see the same observation again. Couple those observations into trajectories. And then the benchmark has queries on the raw data, queries on the observations, queries on the trajectories. And some of them get pretty hard. There's a lot of spatial queries. There's a lot of basically raster-like processing. Jim Gray had a paper a whole bunch of years ago, which was 20 popular Sloan sky survey queries. This was all on the Cook-derived data, so the big difference here is that this is the end-to-end problem as opposed to just queries to the Cook data. So I already said it's a bunch of raw imagery. It's a terabyte of raw imagery cooked into observations, as I just said. Basically, this is a clustering algorithm, and it gives you polygonal spatial data. It's further cooked into trajectories. Trajectories are cylinder-like things that move over time. And it's store all of this stuff and run queries on it. So in the essence of TPC, the regular is a terabyte. It scales up and down to get harder and easier. And there's a whole bunch of parameters, which is like how big an area of the sky do your queries look at. So you can make the parameters make this benchmark much easier or much harder. And so load some data, cook what you loaded, and then run a collection of queries that are on raw data and cooked data. So that's basically the benchmark. The details of the queries are on the poster outside that you can go look at during the break. And what we did was we've run this benchmark. We ran it on MySQL, 10 nodes worth of MySQL with Facebook-style application-level sharding, which was a huge pain in the butt. And on SciDB, SciDB does the sharding automatically. SciDB is about a factor of 15 faster than MySQL on this benchmark. It's faster for a variety of reasons that are all reasonably significant. The first one is First one is you've got to have reasonable spatial database support because there's a lot of polygonal data. And MySQL spatial indexes aren't that good. Part of the benchmark is load. And MySQL is not very good at loading. And that's one thing that users routinely complain about. The other thing is that there's a whole bunch of attribute data, and if you store it column-wise, it tends to be faster than if you store it row-wise. MySQL stores it row-wise. SciDB stores it column-wise. SciDB gets a lot better parallelism, because if you're taking an image and you want to pick out the observations, you want to have a chunking system. Thank you very much.